In section 2.2, we discussed savings account and how you might earn simple interest on those. However, simple interest works with only earning interest on the principal amount or the amount that you deposit into the account itself. As you may remember from Algebra 2, compound interest is a completely different beast. So, if you recall, compound interest is money earned on both your principal amount plus any previous interest. And that's why it can grow so quickly. So, compound interest itself can be calculated in a few different ways. One is annual, so that's once per year. Semi-annual is twice per year. Quarterly, 4 times a year. And daily would be every day, so 365 days a year. Every time interest is calculated, it takes into account the new balance, which again is the principal plus any prior interest. The most common form of compounding is daily. Before we get to the compound interest formula, we're going to take a look at just calculating 3/4 worth of interest using the simple interest formula. So in example 1, Liam deposits $3,500 in a savings account that pays 7% interest compounded quarterly. Now, this 7% actually represents the annual interest, and we refer to that as the APR. APR. So first, we do need to compute that to a quarterly interest rate. So we take 0.07 divided by 4. And then we would multiply that by the principal amount, so 3,500. And since this is just for one single quarter, technically we would multiply by 1, but I don't need to show that. And then that equates to $61.25 in interest. So the first quarter's balance would be the principal plus the interest, making the ending balance $35.61.25. So when we go to calculate the second quarter's interest, we now use that new balance. So once again, we take the balance itself and we're going to multiply by the 0.07 over 4. By the way, I could recognize this simplified and say I'm actually multiplying by a rate of 1.75%. So again, the 0.07 divided by 4, that would be equivalent to this number right here. So then once those are multiplied, that interest comes out to $62.32. So notice the interest amount went up slightly. So we add that to the current balance. And now we are up to $3,623.57. So we're actually going to do that one more time to find the third quarter interest and the balance at the end of the third quarter. So times 0.175% gives us an interest of $63.41. So notice again, the interest did go up slightly. So then the final balance at the end of the third quarter comes out to $3,686.98. Now, just for comparison purposes, I do want to recognize how much interest you would have gotten had this been simple interest versus compound. So remember, simple interest, we take the principal amount and we have our interest rate, so in this case, once again, we have to use the quarterly interest rate, and then times 3/4. So that would have given us a total interest of $183.75, making the total balance after 3/4 $3,683.75. So if we compare this number to this number, there's not a whole lot of difference. It's a little bit more than $3, but that's due to the fact that we didn't start with a whole lot. The interest rate isn't super high, and it was only 3/4 worth of time. So not a whole lot of time has passed. However, it is significant that the amount of interest you earned through compounding was indeed higher than simple interest. Now, imagine depositing $10,000 into a 5-year CD. The account pays 5.2% interest compounded daily. We want to know how much that $10,000 will grow to by the end of the 5 years. So, if you think about it, if we tried to use the process that we just used, that would take a ridiculous amount of time to do, because that means we would be finding the daily interest each day, adding it to create the new balance, and then doing it again the next day. Well, we're talking about 5 years here. That would be over 1,800 days. So we would essentially be taking at least 1,800 calculations just to determine what the final balance of this account would be after 5 years. So, as you know, there is a much quicker way to do this. So, like I was just saying, calculating compound interest using the simple interest formula is tedious when a lot of time has gone by. So, using the compound interest formula, we can turn this procedure into one simple equation. Now, had we been in class together today, you would have taken some time to notice the pattern to create the compound interest formula. I am going to walk through that quickly with you. So, in this example, Jose opens a savings account with a principal of P dollars that pays 5% interest compounded quarterly. What will his ending balance be after 1 year? So, in our compound interest formula, there's actually 5 things to look at. One is the ending balance, another is the principal, the interest rate, the compound frequency, and the number of years. 2 of these are variables, whereas the other 3 things are parameters. So as you can see, we have P, R, and T. And we could easily use that to find the first quarter's interest. So I want you to take a moment and look through all of this math and these calculations to see if you can discern a pattern to help you derive the compound interest formula. You can go ahead and hit pause to take a moment to look at that. So, hopefully something you noticed. First of all, the idea of deriving this formula actually uses something called the recursive formula. So what that means is that we've used previous balances. So for example, in this case, we're using the balance after the first quarter to help us calculate the balance after the second quarter. We're also using factoring to help us derive this formula. So notice in this equation, we factored out balance 1 to create this expression. From there, we actually use substitution to help us write an explicit formula. So what I mean by that, up here we said balance 1 was equivalent to the principal times this quantity. So what we've done in this equation is replaced balance 1 with the principal times this expression or this quantity. But as you can see, we now have a factor that is being duplicated. And when we have repeated factors, we can use exponents to abbreviate the expression itself. So we can continue this idea and take it down to balance 3. So once again, I'm using a recursive formula, finding balance 3 based off of balance 2, factoring out balance 2 to write it as balance 2 multiplied by this quantity, but then replacing or using substitution and replacing balance 2 with what it equals, and that comes from up here. But now notice I have 3 of the same factor. So I have 2 here and then 1 more here. So I can then abbreviate that again with an exponent of 3. So in this case, the pattern will repeat itself the more quarters that I'm calculating interest on. So if I wanted to calculate the interest of after the, let's say the 8th quarter, then I would take principal times 1 plus 0.05 divided by 4 to the 8th power. All right, so something to keep in mind and to discern between the variables and the parameters are what's staying the same and what's changing. So in this case, in all of these equations, even though we're finding different balances after a different amount of quarters, there's always going to be the original principal, our annual interest rate of 0.05 divided by our compound frequency of 4. So those are 3 of our parameters, and then the exponent itself is changing, so that has to do with something with the variable. And then obviously our ending balance itself is changing, so that would be our other variable. So if you saw I accidentally scrolled down, this is the compound interest formula, and we're going to talk a little bit about the exponent itself. So if we go back to our notes, as we said, B equals P multiplied by 1 plus the annual interest rate, which is R, divided by N. So this R divided by N is just converting the annual interest rate to the compound frequency in which we want. Similar to example 1, we took the 0.07 annual rate and divided it by 4 to create the quarterly rate. And then we have to multiply the compound frequency by the number of years. And all that is really telling us is how many times are we calculating interest. So if in the previous example, I said, how much interest is there after 2 years? Well, since it was being compounded quarterly, and quarterly means 4 times per year, then I'm actually taking 4 times 2, and that's why I had an exponent of 8. So, lastly, notice the balance itself is a variable. In fact, it's our output, and the number of years is our input. So that's also our other variable. The rest of these are considered parameters, or we may also call them constants. So once those are established, they do not change. So at this point, we're going to look at a few examples to solidify our understanding of how this compound interest formula is used. So in example 2, Marie deposits $1,650 for 3 years at 3% interest, compounded daily. So in this case, we need to identify that her principal is $1,650, her annual interest rate is 3%, and daily is her compound frequency, so that would be 365. And then T would be 3 for 3 years, and we are trying to find the value of B, which is her ending balance. So that's going to look like, once we simplify, and I'm going to show you, I'm going to simplify the exponent first, just to see how many times is actually being compounded. So over the course of 3 years, this interest would be compounded 1,095 times. So then we would simplify this part of the expression. So over the course of 3 years, we're actually earning 9.4% interest on the total principal. And that comes out to an amount, a final balance in the account of $1,805.38. We're actually going to skip example 3 for the time being and move straight on to example 4. So once again, we have to identify our parameters. So in this first part, 1,000 is P, 8 years is T, 5% is R, and compounded daily, once again, means N is 365. In the second scenario, P stays the same, T stays the same, R stays the same, but notice N is now a value of 2, since we're only compounding twice per year now. So that would lead us to the following 2 equations. And once they are simplified, we get, so in this case, there's just only a slight difference. But once again, the only thing that changed was the compounding frequency. So just by compounding daily instead of semi-annually, it earned an extra $7.27 in interest. So something I've previously mentioned is APR, which is just the annual percentage rate that is often communicated. And that's just the interest rate paid per year, or sometimes if you're being charged interest, charged per year. There is something else called the annual percentage yield. And all that means is it's the simple interest rate required to give the same amount of interest that's calculated by the compound interest formula for one single year. So the reason this is significant is that most banks advertise the APY if you're opening a savings account or something, since it's higher than the APR. If you're opening up a credit card or requiring a loan, they will present it to you as the APR. since that would be lower than the APY. So it's fairly simple to calculate APY. We actually just take the second part of the expression in the compound interest formula. So it's everything except for the principal. We calculate that and then we subtract 1. Because that 1 itself actually represents 100%. So anything over 100% is the amount of interest that's being earned in the single year. So taking a look at example 5, suppose to deposit your money in a 1-year CD at 3.2% interest compounded daily. What is the annual percent yield to the nearest hundredth of a percent? So in this case, R is 3.2. Since we're looking at APY, T is definitely only 1. So we don't even have to factor that in because N times T is still just N. And then since we're compounding daily, N equals 365. So that would give us the following equation. And once simplified, so this means that the APY is that should be 252. So that means the APY is 3.252% as opposed to the APR is 3.2%. So notice this is slightly higher. And for example 6, we take the context that you deposit $8,000 in a savings account with an APR of 4% compounded monthly. What is the balance after 1 year? And what is the APY to the nearest hundredth of a percent? So as always, we are going to identify our P, which is our principal, our APR, which is 4%. Our compound frequency is monthly, so in this case, N equals 12, and T is simply 1. So we have to set up the equation. P equals our principal times 1 plus our annual interest rate divided by the compound frequency raised to the 12 times 1 power. And that simplifies to a total balance of $8,325.93. Now, I can go back and use the APY formula, but since I've calculated the final balance after 1 year, I could actually just take my new balance after a year divided by my original balance of $8,000, and that would give us 1.0474. So what that equates to is 104.74%. But remember, I still have to subtract the original amount because I really only want to focus on what percentage did I increase by. So I increased by 4.74%, and that would be my APY. So notice 4.74 is actually significantly higher than 4% in this case. I could also get around this step by just taking the total amount of interest, so $325.93, dividing that by my principal, and that's going to tell me my APY as well. So again, a few different ways to look at this. All right. So at this point, you can go ahead and start working on continue working on the application questions 5 through, I believe, 11, that all have to do with compound interest.